So in this video we're going to walk through a technique called reduction of order. And so just to remind you, based on the previous video that we watched, we're going to be working with second order linear differential equations for the next several homework assignments. And those have the form a sub 2 y double prime, where a sub 2 is just some function of x, plus a sub 1 y prime, where a sub 1 is some function of x, plus a naught times y, where a naught is just some function of x, and these are going to be equal to g of x. And what we saw in the previous homework, one thing we saw was that if we have a solution y sub 1, then c times y sub 1 is also a solution. So we could take any given solution, multiply it by a constant, where c is just any real number we want, and we wind up with something that is also a solution. And what we saw for second order homogeneous linear differential equations was that the general solution is going to look like this: y equals a constant times y sub 1, where y sub 1 is a solution we find, and c sub 1 is just a scalar, plus c sub 2 times y sub 2, where y sub 2 is just some other function we find that satisfies the differential equation. And y sub 1 and y sub 2 needed to be linearly independent, so their Wronskian couldn't be equal to 0, so we needed a non-zero Wronskian. So those were some of the big things that came out of the previous homework assignment. So reduction of order is going to be a method that we can use when we have a second order linear homogeneous differential equation. And the idea behind reduction of order is that if we know one solution, we can guess the form. So here I have a solution for this differential equation. E to the x, if we take its second derivative, we'll get e to the x. So e to the x minus e to the x is 0. I wrote the equation wrong. So the idea behind reduction of order is if we know one solution, we guess the form of a second solution. And what we guess is that the second solution is going to look like some function of x, u of x. I'm going to drop the function notation on it for simplicity's sake. We guess that the second solution has the form u times the first solution. So for this differential equation, e to the x is a solution. So we're going to guess that the second solution has the form, or that another solution has the form u times e to the x. So we make this as our guess, u times a known solution. And then if this is actually a solution, then when we plug its second derivative in minus u e to the x, it needs to evaluate to 0 or it's not a solution. So what we do is find the second derivative of this function. So I take y prime, and this is just the product of two functions of x. So we're going to use the product rule to take the derivative. We get u prime e to the x plus u times the derivative of e to the x, which is just e to the x. And I see that the e to the x will factor out, so I'm left with u prime plus u. I need the second derivative, so I'm going to take the derivative of this. So y double prime will be the derivative of e to the x, which is just e to the x, times the second function, which is u prime plus u, plus the first function, which is e to the x, times the derivative of the second function. So it'll be u double prime plus u prime. And then what we did is we guessed that this is a solution, so we're going to plug in y and y double prime to our equation. So when we plug in y double prime, we're plugging in, let's simplify this a hair first. This is e to the x. I can factor that off both terms. So I'm going to get u double prime, and then I'm going to get u prime plus u prime. There's two u primes sitting in there, and I'm going to be plus a single u. So I'm going to plug in u double prime, which is e to the x times e to the x times u double prime. I'm going to plug in y double prime, which is e to the x times u double prime plus 2 times u prime plus u, and then we subtract y, so we're going to be subtracting minus u times e to the x, And if this is a solution, if this guy right here is a solution, this is going to need to equal 0. I see that I can factor an e to the x off both of those terms, so I'm going to pull the e to the x all the way out, times, I have a u double prime left inside. I have 2 u primes, and I'm going to get u minus u, so I won't have a u term. So for this to be a solution, this needs to equal 0, and what we know is that e to the x is never equal to 0. For any value of x that you choose, it's not equal to 0. So the only way for this expression to be equal to 0 is for this term to be equal to 0. So we use the zero product property to say one of the two factors must be 0. We need u double prime plus 2u prime to equal 0. And when I look at this, what I want to recognize is that this is really a linear, this can be written as a linear first order differential equation, because I have a function and the derivative of that function. U double prime is just the derivative of u prime. So if I make the substitution, w equals u prime, then that means that w prime will equal u double prime. So I can replace the u double prime with w prime plus 2 times u prime, but u prime, we're substituting it for w, and now I have a first order linear differential equation. And we know how to solve a linear first order differential equation using an integrating factor. So in this case, our integrating factor is going to be e. I'll give him a name. I've already used u. So my integrating factor, I'll call him u sub 2. It's going to be e to the, here's our p of x. The p of x is equal to 2. So it's going to be e to the antiderivative of 2 dx. And this is just going to be e to the 2x. And then the technique for linear first degree differential equations is to multiply both sides by the integrating factor. And if we do that, the result right here winds up being the integrating factor times w prime, the derivative of that product. And then we know to solve this, we just integrate both sides with respect to x. So we integrate with respect to x. We get a constant of integration. The antiderivative of 0 is just some other constant. Take the sum of the constants, it's just going to be a constant. I'll call him c sub 1. And over here, when we integrate the derivative, we just get the stuff inside the integral out. So we get e to the 2x times w. And then I can multiply both sides times e to the negative 2x to get the w by itself. So we have c sub 1 e to the negative 2x. But w is equal to u prime right here. So if w equals this, that means that u prime is equal to c sub 1 e to the negative 2x. And to figure out what u is, then we have to integrate u prime. So we integrate u prime. And we're going to get another constant of integration when we integrate u prime. So I'm going to walk this up here a little ways. I need some space. So the antiderivative of u prime is u. U equals, the antiderivative of this is going to be negative c sub 1 over 2 e to the negative 2x plus our c sub 2. Now remember, what we did is we guessed that the solution looked like this: y times u times y sub 1, or u times e to the x. So that tells us that our solution is y equals negative c sub 1 over 2 times e to the negative 2x plus c sub 2. That's our u times e to the x. So this is a solution to that differential equation. I distribute the e to the x into the parentheses. I'm going to get negative c sub 1 over 2 times e to the negative x plus c sub 2 times e to the x. And what I'm going to notice is that e to the x, which is a solution, is showing up right here. So remember that if you have a solution, you can choose any value for the constant. So I can let if c sub 2 equals 0 and c sub 1 equals negative 2, then I'm going to get that e to the negative x is also a solution. And you could verify this by substituting into the differential equation. If we put e to the negative x in for y, and then we take the second derivative of e to the negative x, first derivative is going to be negative e to the negative x, and the second derivative would be e to the negative x, and you get e to the negative x minus e to the x is 0, so it is a solution. And then all we need to do is verify that what we have is linearly independent with the e to the x. Is e to the negative do e to the x and e to the negative x form a linearly independent pair of solutions to the differential equation? And to check that, we would just check the Wronskian, right, from the first homework assignment in this this new section. We're after two linearly independent solutions, so we check the Wronskian. So the Wronskian is going to be, we have e to the x and e to the negative x, and then we take their derivatives. So the derivative of e to the x is e to the x, e to the negative x is negative e to the negative x, and then the Wronskian is just going to be e to the x times negative e to the negative x, which is just negative 1, minus e to the negative x times e to the x is just 1, is negative 2, which isn't equal to 0. So we know that e to the x and e to the negative x, both of which are solutions to this equation, are linearly independent. So the general solution to the differential equation is going to be y equals c sub 1 times e to the x plus c sub 2 times e to the negative x. So I'm going to do one more worked example, and then in another video I'll do one more video with another worked example. Then we'll do a third video where we show that there's a formula for doing this. But in the homework, the expectation will be that you don't use the formula, that you work through the process like I did here each time you solve the differential equation. We want to solve them from first principles so that the concept gets kind of ingrained into our long-term memory.